Hello everyone, my name is David Mora Herrera, and today I will present you some status about my research work. This is by International Material Research Congress in Cancun, Mexico for this year, and this is the title of my research work: Path Towards the Performance Upgrade of lead-free perovskite solar cell using copper sinting germanium sulfide as whole transport layer and theoretical simulation approach. This is the abstract and introduction. Recently, formaldehyde iodine perovskite has been emerging as promising candidate for lead-free perovskite solar cell. However, a limited power conversion efficiency was achieved when the conventional titanium oxide and SB4 were selected as electron and hole transport layer, respectively. So, employing numerical modeling for this ether structure, we noticed that the conduction band offset between the titanium oxide perovskite and the valence band offset between the perovskite and SB4 layers are suboptimal, resulting in a limited power conversion efficiency. So the principal objective of this work is replace the electron transport layer and alternative electron transport layer, respectively. So as we know that the copper sinting sulfide used in absorber layer in solar cells is very important. This material presents low toxicity, abundant elements, normally exhibit p-type conductivity, also present an optimal bandgap of 1.5 electron volts and high absorption coefficient. So to improve the Kesterite efficiency, several elements has been tested as dopants and allowing candidates, and more recently some of extremely positive results of the extrinsic and allowing doping had been obtained in using germanium. The bandgap tuning of the copper sinting sulfide invisible region can be effectively performed by replacing tin with germanium in this case. And this material or this compound is very important. This is the inorganic material. So the inorganic materials like this is very important for apply it in perovskite solar cells as whole transport layer, because this material presents high stability, low cost, and adequate electrical properties, and their facility synthesis. So the combining effect of material simulation and modified device exhibit an experimental power conversion efficiency of 17% and open circuit voltage of 0.75 volts. And this is the methodology. We use the solar cells capacitance simulator SCAPS 1D with this version, and the baseline parameters for different layers following the experimental reports solar cells by Lee as our reference systems, and we took advantage of the admittance spectroscopy including in the SCAPS to determine the equivalent circuit. So this is in this figure show the schematic representation on the device configuration using the experimental study performed by Lee. And the other hand, in this figure we show the proposed designing containing alternative electron transport layer and the whole transport layer and alternative back contacts. And this is the important configuration in perovskite solar cell. In this figure we show the comparison between the simulation and experimental results. This is a UV curve, and this is the flat band energy diagram for experimentally reports solar cells by Lee et al. So a good matching between the simulated and experimental results, confirming the accuracy of our model like this is very good. And this is the most important, and this is the results. And to investigate the effects of the germanium concentration of the photovoltaic parameters of perovskite solar cell, we simply replace the organic whole transport layer SB4 by inorganic p-type copper sinting germanium sulfide. So in this figure, the UV curves of the device is shown in this figure. We observe the primarily difference in photovoltaic performance between the whole transport layer is the high open circuit voltage obtained with copper zinc and germanium sulfide for any values of X, or for different germanium content in comparison with the SB4. We observe the open circuit voltage increases and the short circuit current also increases. So the open circuit voltage mainly depends on the energy difference between the valence band edge of the perovskite layer and the HOMO level of whole transport layer. A deeper HOMO level to the valence band edge of perovskite results in a significantly larger open circuit voltage. So this is in this figure show the Nyquist plot with different whole transport layer for the DC bias voltage close to open circuit voltage under illumination condition. This is the illumination condition at one zone. And the impedance spectroscopy parameters were obtained by fitting by Nyquist plot with the equivalent circuit like this. The recombination lifetime and we observed that in this table is very important. The impedance spectroscopy is very powerful technique to study the resistivity and the capacitance behavior for solar cell devices by applying an alternative voltage. So we observe different parameters for different whole transport layer by SB4 and different germanium content for our alternative whole transport layer. And this is the first parameter, is the series resistance. This is due to the wire and contact resistance. This is the capacitance whole transport layer. This is the geometrical capacitance related with the carriers accumulated at the interfaces. The resistance whole transport layer, this is the describes the contact resistance at the whole transport layer perovskite and the perovskite electron transport layer interfaces. This is the capacitance in bulk. This is the chemical capacitance associated with the photo-generated carriers stored in the perovskite layer, and this is the recombination resistance in the perovskite layer. To determine the important parameter, this is the recombination lifetime. So the recombination lifetime is recognized as a crucial parameter to describe the recombination phenomena inside in the device. A higher recombination lifetimes indicates that the carriers recombine with more difficulty, particularly using copper zinc germanium sulfide without tin, boosting the recombination lifetime. In this case, we observed that the recombination lifetime is very, very high. So to observe this behavior that the open circuit voltage increases, we observe the close-up of the energy band diagrams for the valence band offset between the whole transport layer and the perovskite layer interfaces. We observe that despite the energy band offset between the SB4 and the perovskite layer is very high, but when replace the whole transport layer by copper zinc and germanium sulfide with different germanium content, this barrier is very low. So we observe that the open circuit voltage, consequently the open circuit voltage increases. And this is the architecture of the proposed perovskite solar cell with different maximum efficient, and this is the alternative whole transport layer is the copper zinc germanium sulfide. This is the alternative electron transport layer and alternative contact in the perovskite solar cell. So with this replacement with alternative electron transport layer and contact to optimization of the band gap and electron affinity in perovskite layer with these contour maps or contour plots, and we observed that the perovskite solar cells for different values of the band gaps and electron affinity, we observed the optimal parameters for perovskite solar cell, because for this perovskite solar cell reports different values for band gap and electron affinity. So this is very important, and this is my results. So this is the best device configuration. Finally, in this figure shows the device structure of the champion solar cell. The combining effect of our proposed modification could be enhance the simulated efficiency from 4% to 17%, and this is the best performance solar cell. And we observed that this perovskite solar cell is lead free, and alternative electron transport layer, and alternative hole transport layer, and alternative contact. In this case, the alternative hole transport layer is inorganic compound. As conclusion, we found that the enhanced efficiency of copper, zinc, and germanium sulfide is largely contributed to the cliff type of the conduction, the valence band offset, at the hole transport layer and perovskite interface, with a favorable offset which facilitated the hole extraction from the photoexcited perovskite layer. And this is the reference, and in this case, in this link, we observed this link, and this is a publication of this work in an important journal. So this is my work, and thank you so much.